We've talked about one-dimensional arrays, just one line of data, but we can also have arrays with 2 or more dimensions. In this video, I'll talk about rectangular arrays. The next one, we'll talk about jagged arrays. We can declare a 2-dimensional array just by specifying how many rows and columns we want it to have. We call these rectangular arrays. The rows and columns are numbered from 0, just like our one-dimensional arrays were numbered. We can index any individual position in the array by specifying its row and column. So this assignment statement will put a 42 in the position in row number 2 and column number 3. Just like one-dimensional arrays, we often want to do something to every position in the array. For a 2-dimensional array, a walking through the array loop is 2 nested loops. The inner loop walks across the columns, and the outer loop walks down the rows. That generates a sequence that indexes every position. It starts with row 0 and runs through all of the columns. Then it makes row B1 and runs through all the columns again, and so on through all of its rows. This is the result of that loop. Every position's value is 10 times its row number plus its column number. I dumped the stack so that we can look at that. We can find our data here. The compiler actually stores it as a one-dimensional array. I've colored the rows so that you can find them. Row 0 is first, then row 1, and then row 2. That way of storing multidimensional arrays is called row major order. That means that it stores all of row 0, followed by all of row 1, followed by all of row 2, and so on. With it stored that way, we can calculate the address of any individual entry from its row and column number. It is the address of the array plus its row number times the row size plus the column number. Let's think about what that's doing. It starts at the beginning address of the array. Then it uses row number and row size to skip past all of the preceding rows. Then it adds our column number to get to the right position in the row we want. For example, let's do the math for position 2, 3. Row times row size would be 2 times 5. Adding 10 to our starting address gets us past row 0 and row 1. And then adding the column number gets us to the position we want. We need an example to motivate why we're playing this game. Suppose we're football fans and we want to keep track of passing yards per quarter for an entire season. If we assume that our season has 9 games, this is how I would create an array to hold our data. 1 row for each game and 1 column for each quarter. For example, the third game's second quarter would be here, row 2, column 1. Remember, indexes start at 0. Let's fill that with some data. For a 2-dimensional array, the initializer has extra curly brackets separating the rows. With this, the third quarter of the 5th game has 12 passing yards. When you do this in CLion, it adds some explanatory information that makes it much easier to read. Now that we've stored our stats, we can calculate some interesting summaries. For example, we could ask, what is our average passing yards in the 4th quarter? For that, we need to walk down the column for that quarter, adding to a running sum, and then divide by the number of games. That's just a walking through the array loop that walks down the games. We always use 3 for the column index because we wanted the 4th quarter statistic. We could also calculate the average passing yards per game. For that, the strategy is to get the sum for each game and add them to a running total, and then divide by the number of games. The outer loop is walking 1 row at a time, 1 game at a time, and the inner loop is walking across the quarters of each game and adding them up. Add that game's total to a running sum, and when the loops finish, we'll have a sum of all the games. Just divide that by the number of games to get the average. Now, I've done all of this with 2 dimensions, but there isn't a limit on that. We could have as many dimensions as we want. Suppose we want to keep our passing yards data across 5 seasons, where every season has 9 games. We could add 1 more dimension for the season number. That makes our data like a cube, one plane for each season, stacked next to each other. When we do that, even though it feels like there are 3 dimensions, C is still storing it as a one-dimensional array, putting the planes in order and doing the math to compute where a particular position is stored. All that is good, but there's some real limitations to this strategy. Suppose we want to store stats for overtimes. Well, we could make the grid have 5 columns, an extra quarter for the overtime. But what do we do with games that don't have overtimes? If we store a 0 in that last column, does that mean there wasn't an overtime? Or they didn't complete a pass during the overtime? And what if a game has multiple overtimes? We have a similar problem if the schedule has buys in it, so that there are weeks when teams don't play. The bottom line is, there are times when we want multidimensional arrays, but we don't want them to be rectangular. We'd like each row to be able to have its own length. We call these jagged arrays, and we'll talk about that in the next video.